Alright, so this is the 2016 NCEA Level 2 Physics Electricity exam. We're going to be looking at question 2, which is about static electricity. That's going to use this equation here, which includes the electric field strength, the voltage, and the distance. We're going to use this equation here, where the force equals the electric field strength times the force on a particle equals the electric field strength times the charge on the particle. This equation here, which is about electrical potential energy, and that equates to the electric field strength times the amount of charge on the particle times the distance that the particle moves within the field. Well, it's really up or down the field, across in the direction of the field lines, I think is the key here. And we've got this one here, which is the kinetic energy, which is proportional to the mass and the velocity squared. This equation here is also relevant, despite being in a different place. This is the voltage being related to the electric field strength. No, sorry, it's not. The change in energy and divided by the charge. Really, this is related to one of the other equations. This one and this one put together, I think. No, this one and this one put together. So, let's have a look at the question. The reason this one becomes confusing, just before we go on, the thing that can get confusing here is you've got electric field strength, energy, electric field strength. What about this one? What's that one? And so this one here is energy again. So yeah, there's no change in electric field strength. So this is change in energy, right? Now let's have a look. The question. So exam question is about static electricity. The first part of the exam question is about these this X-ray machine. In an X-ray machine, a heating element, that's this bit here, releases electrons from a negatively charged plate called the cathode. So this is a hot cathode. The electrons are basically pumped out because they get highly energized by the heat as well as by it being negatively charged. So that the combination releases electrons into a little cloud around here. And the electrons in that cloud are repelled from the negatively charged cathode, and they're attracted to the positively charged anode over here. So they accelerate across this gap, and then they hit this plate. And when they hit the plate, hitting the plate makes them stationary, and they interact with the metal on the plate, and that can release X-rays. We don't need to worry too much about the X-rays themselves. We're looking at how this electron accelerates across here to create a highly energized particle that is then capable of releasing the X-rays. So without further ado, let's look at question 1. You can see here we've got 20,000 volts between the cathode and the anode, so that's quite a big power supply. Alright, all this is done typically in a vacuum tube. The diagram on the right shows the arrangement to accelerate electrons as they leave. So this is just kind of thinking about this area here. The electron leaves the cathode and then it's going to accelerate across to the anode. Calculate the electric field strength between the plates and state its direction. So we need an equation. We've been given a distance and a voltage and asked for the electric field strength. So I think we're going to use this equation here. I'll be able to scroll more quickly. How am I going to do that? Yeah. Okay, let's get this right next time. So E equals V over D. And as we can see, if the voltage is higher, the field strength is higher. If the distance is higher, the field strength is lower. So V equals 20,000 volts. D equals 0.050 meters. E equals 20,000 divided by 0.050, which is 400,000 volts per meter. You can have this as volts per meter, or it could be newtons per coulomb, because you can use this to work out charge, but it's easier just to leave the units as the volts per meter. So that was in volts and that was in meters, so it's volts per meter. State what type of energy an electron would have at the cathode. So that's the cathode here. This is just as it departs, and what would happen to that energy. So at the cathode, so we'll just start with this bit, state what energy it has. The electron has electrical potential energy. And what would happen to that energy as the electron moved toward the anode? The electron accelerates, this isn't about energy yet, toward the cathode, toward the anode rather, increasing speed, gaining kinetic energy. So as it gets faster, it must be gaining kinetic energy, because EK equals a half mv squared. And so what's happening to the energy? Electrical potential energy is converting into kinetic energy. My pen's doing weird things, I'm not quite sure why. Come on. My PDF software is doing some not very useful stuff, sorry about that. Calculate the speed of the electron as it reaches the anode, the positive plate. Okay, so EK equals a half mv squared. So this is where we're going to get our speed, okay? And EP equals EQD, or we could also use that as V equals E over D. So the energy change equals the voltage, sorry, it's E over Q. The energy change equals the voltage times the charge. So they really come out as the same thing. The field strength times the distance gives you voltage. So they work out the same, these two equations. We're going to use this one. So firstly, we're going to work out the potential energy. So EP, and the key thing that we've just talked about up here is that EP is turning into EK. So we can use, by the time it reaches the plate, that's when all of the potential energy is converted to kinetic energy. So that means that we're going to set EK equals EP. Now EP equals, the electric field strength was 400,000. The distance was 0.050. The charge is an electron, 1.6 times 10 to the minus 19 coulombs. We do that calculation. We get 400,000 times 0.050 times 1.6 exponents negative 19. Make sure you use your exponent button properly on your calculator. You get 3.2 times 10 to the minus 15 joules. So EK equals 3.2 times 10 to the minus 15 joules. So that's that key piece of physics, is that that's what the EK is, and that equals half times m times V squared. So we've got, now let's just start working this out. We want V, so we're going to go for, do a bit of rearrangement. We also want to substitute our mass in. Where are we going to get the mass from? That's what was it in the question? Mass of an electron, here it is. 9.11 times 10 to the minus 31. 9.11 times 10 to the minus 31 kilograms. So now we've got the information we need. 3.2 times 10 to the minus 15 equals a half times 9.11 times 10 to the minus 31 times V squared. V squared equals, and I'm going to 3.2 times 10 to the minus 15 over a half times 9.11 times 10 to the minus 31. Now this is where you've got to be super careful. You're dividing by a number that's going to have a large negative exponent. So put all of that in brackets, or carefully use your exponent button, or do it in multiple steps. Any one of those. I'm going to use brackets. Well, I'm going to use my exponent button properly as well, but I'm still going to put brackets around it because that's the way I was taught long ago. Just do a quick check, and I get an answer. V squared equals 7.0252 times 10 to the 15, and of course that's V squared here, so what do I need to do? I need to square root it. V equals, so square root answer, and I get, and then I want to put this, it's given me a number with lots of digits, so I'm going to press the E and G button to put it into some sort of exponent form. 83.8 times 10 to the power of 6, and it's a velocity, so it's going to be in meters per second, or meters per second. Now that's to 3 significant figures. If I'm being really good about this, what am I looking for? I've got 3 significant figures up here for the mass and so on, and I've got 2 significant figures here, and you can argue only 1, but it could be 5. It's hard to say there, so I'm quite happy to leave it as 3 or as 2, either or. Okay. Part D. So we change now away from the X-ray tube, and we're looking instead at Millikan's experiment. So this Millikan's experiment, he used this to determine the charge on individual electrons. If the oil drops are small enough, then the force of the electric field on these oil drops, he could work out and find that the electrical charge that was producing that force was quantized. That is, that it came in fixed kind of parcels of force. Very complex experiment in the form that it was made, because the oil drops were not very consistent, so we had to measure the size of the oil drops and calculate their mass, as well as twiddling knobs on his power supply to try and levitate these oil drops in this gap here. So that's what's going on. So if we just think about an oil drop for a moment, it's subject to the force of gravity pushing down, and if it is a negatively charged oil drop, then it would be being pushed up in this plate here. So if it gains, say, 2 electrons, then this negative plate is going to be repelling it. It's going to be being attracted up here, and it's going to experience a force due to the electricity pushing it up. And if it's levitating here, that's because, if it's stationary, that's because it's not moving. No, it's not because it's not moving, of course that's right, but it's experiencing a net force of 0, so the F electrical equals Fg. Right, that's what we want to think about. So, in your comprehensive answer, you should identify the forces acting on the oil drop. That's what we've talked about here. Tick, we can do that. Describe how the forces can combine to cause it to be stationary. Just let me finish, and then I'll do it. And then that's going to, so it doesn't accelerate. So we want F net equals 0. That's what we're going to use there. And explain what type of charge the oil drop must have in order to remain stationary. So this is the idea that if it is a negatively charged particle, it's going to produce a force upwards. So negative. Okay, so those are the things I'm going to try and include. But I've still got to write an answer. I can't just chuck those in there. So gravity is acting downward. F equals mg. Electric force is acting upward, and that is going to be F equals EQ. Let's just check that I've got that formula right. So we go back and we always have a look. Always worth double checking what you're doing. There it is, F equals EQ. Takes no time to go and check. Loses your marks, you get it wrong. So F equals EQ. So proportional to the field strength and the charge. Okay. I'm not sure what's up with my pen at the moment. I think my computer is struggling to run this application while recording the video, unfortunately. Come on. The direction of the electric force depends on the charge. So it depends on the charge. An upward force to levitate it will only be produced on a negatively charged particle. Why? Because the lower plate is negatively charged. Why am I losing my text? So to remain stationary, the net force must equal 0 if G must equal EQ. I'm sorry about the text all disappearing like this. Alright, let's have a look now at the marking guide, which I had. Alright, so let's see if we can fix this up now. Well, let's see if we can mark it. So let's see. For the part A, you need, it's only with an achieved, no matter what you do to it. You can do no better than that. 400,000 volts per meter. Ooh, you're supposed to provide the direction and state its direction. So I didn't do that. Interesting. From the cathode to the anode. Now, down here, we've talked about, no, we haven't in this one. We've talked about how it accelerates toward the anode. I wonder if they would accept that once you got to part C, I'm not sure. Nonetheless, so yeah, force, because it said and state its direction, I just forgot. So I didn't get the achieved there. You need both tick tick for A. Right? So if you didn't state the direction, it's because you didn't check carefully that it was required. Part B. You need to name both energies. You need to name one energy at least for achieved. Well, we've got that. So it's achieved here or here. You need to state both energy and imply that one changes into the other for your merit. So it is converting to get you your merit. Okay. What about next? Let's have a look. Part C. Let's hope we got the right answer. Looks about right. So, correct answer, 80. So, and this is where you've got difference in things. So they've got 8.39 times 10 to the 7. I've got 83.8 times 10 to the 6. So that's the same answer. So tick that. That would be worth, according to this, correct answer gets your merit, right? But what about if you didn't get that answer? What could you get? The work done is calculated correctly. So the work done is this bit here, EP. So this would get you an achieved. The understanding that kinetic energy equals work done. So this idea here, or this idea here, that gets you an achieved point as well. Or incorrect work done and completely incorrect, or consequently incorrect speed. So if you get this wrong, but you follow through this correctly, you might also get an achieved point. So there are some miscellaneous achieved points possible, but a merit is the best you can do overall for that. And the last part, Millikan's experiment. Why is my text all completely in the wrong place? Oh no, it's not actually Millikan's experiment yet. Yes, it is. Oh dear. Let's just see if we can get it to redraw completely. Nope, it's all completely out of whack. Bring it out again. I don't know what is up with my software today. It's really not doing the job. So this is my answer for Millikan's experiment. In any case, let's have a look at it. So we've got it here. We can still mark it. The forces, so they say that the important stuff here is the forces acting on the drop are downward weight force and upward electrical force. These two forces must be balanced so that as the oil drop is stationary, for the electrical force to be upward, the type of charge on the oil drop must be opposite to the charge on the top plate. It's interesting because it actually told you what the charge on the plates was, so that implies that it is a negative charge. Identifies the two forces, so achieved points. Identify the two forces. So these two here gives you an A. Saying the forces must be balanced was also an A. And top plate should be positive and the charge on the oil must be negative, or vice versa, is an A. You explain that the electrical force must be, so for merit, you need identifies the forces and that they must be balanced. So these two here would give you an M. And for an excellence, you needed explain that the electrical force must be upwards to balance the downward weight force as the oil drop is stationary, and for the electric force to be upwards, the charge on the oil drop must be negative. So basically, the whole lot gets you your E. E, let's leave that bit out of it. Okay, so there you go. That's question 2 of the 2016 electricity exam.